In this lecture, we start with something very important. And before I go into the details, I would like to give one example. So let us see what this is all about. Suppose you have a situation in front of you wherein the issue that we face is suppose one of our friend went home from school on his car. Suppose he starts from here and he reaches home somewhere here. And say on the road, the maximum speed allowed is 80 km per hour. But somewhere in between, he is fined by a policeman for overspeeding. And if I ask you the question, where you think the friend crossed the speed limit? And what you observe is that you are given total distance covered and total time taken. Suppose from here, starting point to end point, the distance is say 50 km and the time that he took total is 2 hours. Now if you wish to calculate or rather find where he crossed this limit, and say if you want to find average speed is 50 by 2, which is 25 km per hour. Naturally, with this average speed concept, we cannot say where he crossed the limit. So this average speed is not beneficial to us in this situation. So what we should do? So it's the time for all of us to think, and I suggest that you stop the video here for a minute or two and think how you can find where the person's oversped and crossed 80 km per hour limit on his way to home. So this is an important question, and you know that average is not giving you an idea. So what should we do? The journey is in front of you. It started from say this point. So what we can do now is, if the distance is 50 km and the total time taken is 2 hours, then we should break this journey and analyze small portions of this journey. For example, if I break 2-hour journey into 4 parts, say 30 minutes each, and I find that the person was after 30 minutes here, next 30 minutes say he was here, next 30 minutes say he was here, and finally he is here. And now you can check this duration and see whether he crossed that speed limit here or not. Suppose in this part of the journey he completed say 10 kilometers, and then in this say 20 kilometers, and in this say 10 kilometers and the last 10 kilometers. So in the first part journey, the average speed is 10 kilometer upon this, because it is 30 minutes 0.5 hours, is 20 km per hour. Similarly, you can find for the second part. So second part average is 20 upon 0.5, which is 40 km per hour, and the third part and the fourth part average is same, which is 20 km per hour. So naturally, still it is not clear where he oversped. So what is the next step? So the next step is to break this into 15 minutes components and then analyze each portion the way we have done earlier. Even if that doesn't work, then we have to break it up into further portions of say 1 minute each. And the moment you do, you will come across one particular region, say this region, where you will see that the average speed for this small interval is say greater than 80 km per hour. And naturally, you can say this is the region where he has oversped. So what you saw that in such physical situation, we actually to come to the right solution, we break large, say something to very small. And the moment we do this, we actually come to the right answer. So this is one physical situation when we divide something into small parts to analyze a physical situation. For example, here the physical situation was where the person oversped. So this is one logical way in which we think, where we convert large something into small parts. And this in mathematics is known by something which we will discuss. This division into small parts is considered something very important and forms part of very important branch of mathematics. We'll see this later. We have a different situation now. Suppose you are given daily money that you and your friend gets from your parents, and finally you have to say who gets more pocket money per month given the daily spent. So for example, day one, you and your friend, how much they have got. Say day one, this is day, you got from here, you say let's say 5 rupees and your friend got 10 rupees. Day 2, you got say 15, he got 25, and the entire month spent is given. How you will know who gets more pocket money? Once again, it's time for you to think, and you can stop this video here in case you are not able to intuitively guess what is a way out of this situation. So situation is pretty obvious. You are given first, second, third till say 30th day pocket money that you got or you spent, and your friend is also given this way. Suppose you got 5 rupees, you got 10 rupees, and that way you are given for 30 days. So how do you compare monthly pocket money given the daily spends? Naturally, it's pretty obvious that you will say, I will add up small things, daily spend, and suppose you are getting 1030 here and you are getting 2500 here. It's pretty obvious that your friend is getting more pocket money. So in this situation, what you see is small things are added up to give a large thing. Now this is a process which is applicable here. When we add up small things, we reach large quantity. In the previous case of your friend leaving home and overspeeding, it was we were adding we were breaking it up large thing into small pieces, whereas here small things, which is the daily pocket money mentioned here, is added up for a month to a large number to compare. So one way of comparing was dividing something into small pieces, and the other was actually adding small things to large. These two different approaches are used in mathematical analysis that you will soon see in much detail. So it's pretty obvious that in some situations, to analyze a particular phenomenon, we make very small pieces by dividing given large piece. This process is called differentiation, and it is one part of the branch in mathematics called calculus. The other opposite approach is when we make a large piece by adding small pieces together, and this addition into a large piece in the language of mathematics is called integration, and is the other part of we start now with formal definition of calculus. We are all familiar with graph plotting. The fundamental idea of calculus actually emerges from plotting the graph. So let us understand how we plot graph. Components of graph plotting are on your screen. We need meaningful title. Then we need variable on x-axis, variable on y-axis. Variable on x-axis is called independent variable, and variable on y-axis is called dependent variable in the language of calculus. The steps in graph plotting. Say we are plotting your distance from home against time. So the title of the graph will be distance from your home, and what we are trying to find out is against time, therefore we write time there. Unit will be of time will be in hours, and what we are measuring against time is your distance from home. So that is the straight line distance covered, and the units naturally would be in the length units. So the independent variable is time, and the dependent variable is the straight line distance covered from the initial start, and this is how you plot on the graph. To illustrate this point, we take some dummy data. We say that x-axis starts at 0, and after every 10 units there is a tick mark on x-axis. Similarly, y-axis starts at 0, and after every 10 units there is a tick mark. Now we take x and y values, and the most important point is that for a given time there can be only one position. This is the fundamental idea of calculus. You can have only one independent variable, rather one dependent variable for one independent variable. So for one time you can only be at one position. This is critical point, and you must remember this. So now I'm plotting, and you can see for every one independent variable there is only one dependent variable. We had a straight line in this case. Y is called output, x is the input. Dependent variable is called function of x, where x is the independent variable. Small quiz for you. Can you tell which one is not a function here? The obvious answer is on your screen, and you can easily understand it. We now discuss a very important concept called slope of a line or a curve. Slope of a line or a curve, at any point the tangent on the curve is actually delta y upon delta x, or change in y upon change in x, which is y2 minus y1 upon x2 minus x1. And here is a illustration how we are finding the slope. We are simply changing y here, and you can see y2 minus y1 is changing, and the ratio y2 minus y1 upon x2 minus x1 is giving us the slope, which is changing and is showing now it is a negative slope because you have a negative x, and y2 minus y1 upon negative x is naturally a negative slope. This is again a positive slope, and finally we reach fourth quadrant where again it is a negative one. Let us have a practical example where we can understand this. Say you are coming back from your school and we wish to analyze your driving behavior on the way. So how do we do it? That is a question. So let's say we plot your distance from your home against time. So what we are doing is, as you are moving, we are timing for every small interval, and you know earlier that we call this process as differentiation because we are dividing the entire journey into small parts of 1, 2, 3, 4, 5, 6 seconds, etc. So the car is moving, and this gives you a graph plotting which we have discussed earlier. Now if you remember, speed is distance upon time, and if you take time as one unit, then speed is nothing but the distance covered in that one unit. So in second from 2 to 3, body has moved from 2 meters to 3 meters. So 3 minus 2, which is 1. So 1 meter per second is the speed in this particular interval. And this speed is represented by the green rectangle. With the same logic, you can find speed for the entire journey. And in this particular case, the speed was constant, and you can see the slope of this line also constant. It's a straight line. You can plot this speed on a different graph, and speed, as we know, is distance covered in 1 second. So we have plotted this one after another, and we find the speed is constant. Against time. Now if you just pull back these squares of speed that we plotted on the other graph, you get distance against time graph once again back. And if you add the distance covered in each second, it will add up to the total distance from your home to the school as shown in the figure. So it's a very simple idea that complete distance was broken up into small parts to analyze speed in each second. Now look at the scenario once again. The same car, you are coming back, say from your school to home. And now we see a different thing. We are noticing that you are covering greater distance in every second. Yet the distance covered in every second remains constant. In other words, the slope, which is y2 minus y1 upon x2 minus x1, remains constant. And if you take the time difference x2 minus x1 as 1 unit, you see that it is covering 6 minus 3, which is 3 units. So you will say the speed here is 3 meters per second. But in the entire journey, speed is constant, or y2 minus y1 upon x2 minus x1, as seen earlier, is constant all throughout the journey. Once again, you can plot the speed against time graph and you will again get constant speed against time, but in this case the speed is greater than the earlier case that we have seen. It is 3 units per second or per unit time. You can put these small units back and you can add up to get the distance, total covered distance back once again. So what you are noticing is the process of dividing into small intervals and then adding up. For instance, another situation. Here the car is moving, but after every second it covers, say, different distance. You can very well see that y2 minus y1 upon x2 minus x1 is changing for every second, and this, another word, means actually speed is changing because y2 minus y1 is the distance covered and x2 minus x1 is the time, and time here is independent variable and distance covered is dependent on time, which is dependent variable. So if you see the rectangles, the green rectangles, where the speed is actually increasing in every unit time initially and then it decreases, and finally you see yellow rectangles where y2 minus y1 is negative, means body is moving backward. So whenever y2 minus y1 is negative, it means negative speed or body is coming backward. You can add up these small rectangles which represent distance covered in unit time. It will give you at any instant the straight line distance of body from origin, and yellow will be subtracted. It's a moving backward thing. So when body comes back, the yellow portion writes off the green thing, and this is the net displacement from origin. So you have once again the graph of the speed of the object against time that you have obtained by dividing the total time into small intervals, and that process of dividing is something very important that we have discussed. Now interestingly, see, the corners are sharp in such a graph. Sudden changes of speed is happening. After 1 second, suddenly the speed changed, and that's why the slope changed. In such a graphs, always you'll have sudden jerks. For example, here y2 minus y1 upon x2 minus x1 is the speed or the distance covered upon time, and for every second you can see the sharp corners are there. But if you want to make this smooth, then you have to further divide this time into much smaller units. So here, for example, we are adding these rectangles in the case given. In any case, when you add up these rectangles, small rectangles of this kind of a situation, they will add up to the net distance covered from the origin. And this is the fundamental theorem of calculus. Any variable like distance here, if divided by taking small variation of independent variable, gives a better picture in those small interval, and when we add up we get the independent variable back, which is the distance in this case. Now if you want to remove complete sharp corners, then you have to take a very small interval in time called dx, and d comes from delta. Delta means the change. So on horizontal axis change in x, on vertical axis change in y, but when you write d, it means very small changes in y, which is dy, and very small change in x, which is dx, and when you divide dy by dx, it gives you the slope, and the slope is nothing but the speed in this case, and this is called derivative of y with respect to x. So whenever you plot the slope where independent variable is taken as very small, then corresponding dy and the slope of dy by dx is called derivative of y with respect to x. This, in other words, is nothing but, if you see the white line here, it is nothing but a slope at any point. So dy by dx is nothing but the slope or the tangent which you have, slope of the tangent at any point in the line. So white line, you can see the slope is changing, it is decreasing, tan theta is decreasing as you are moving forward, and at this point the slope or the tan theta, now it becomes 0. Now tan theta is becoming negative, and therefore slope is becoming negative, and if slope represents speed, then speed is becoming negative, and that's how we interpret the slope in any graph. Now we are considering again the situation where we had large step increase in speed, or where your independent variable was changing by large amount. So you will have abrupt changes as shown, and the curve will no longer remain smooth. It will once again become sharp at the edges. You can see from the figure here. And the slope represented by a white line will abruptly change. It is changing abruptly now, and you can say dy by dx is changing abruptly when your time interval is large. This means speed is changing abruptly in this example. And the top shows your speed graph where there is an abrupt change. You can see there is a jerk motion in the white line. However, when does it happen the speed changes smoothly? That again I repeat, that is when you divide the time into very small intervals of time, which we called dx, and dy by dx is the speed which we can term as function of x also. So at any x or at any time, you can say fx, which is the function of x, or the speed at different time. And here the speed is negative, or the fx is negative. So fx is nothing but dy by dx. And since distance is equal to speed into time, and distance therefore is speed into time. Speed is dy by dx into time is dx, small change in time. So small distance covered will be dy by dx into dx, where dy by dx is speed in that interval. So distance covered in any small interval is fx, or the dy by dx observed in that interval, into dx, which you can see very easily from the area of this rectangle. Any one rectangle is this. Green colored, light green shows that rectangle or the distance covered. Fx is speed at any x or the height of the rectangle. Dx is the width or the dt or the time. And when you multiply the two, you get simply the dy or the area of the rectangle. So area of one rectangle, small distance covered in small time, dx is fx dx. But if you want to obtain the total distance covered, then you have to add up all the areas of these small rectangles, or we sum them up, or we integrate these small rectangles to get total distance covered. So what you are seeing is nothing but a process of dividing something in small intervals, and if you want to obtain something back, then you integrate, which is sum of those rectangles, and this sum is shown by this symbol which we call integral. So this light green colored symbol is nothing but the symbol of sum. So whenever you say integral fx dx, means you are summing up the small areas shown in the given situation. And the given situation is distance is the dependent variable and time is an independent, but you can have any variable in any kind of other situation. Naturally, green is the positive area or the positive distance covered, and yellow is the negative area or the negative distance covered. So total area, say if you want to compute the distance covered from 0 to 10 seconds, then you start summing up from 0, which is called the lower limit of the integral, and 10 is the higher limit of the integral. And since we are computing between two fixed time, this integral is called definite integral. So summing up between fixed lower and upper interval or upper limit is called definite integral. So in a way you are saying what is the distance covered between 0 and 10 units of time. You started observing from 0 and 10 is your final observation time. So the integral of all small rectangle then gives you the total area or total distance covered.